Today we're going to explore one of the most fascinating phenomena in materials physics, the strain storage paradox. This is a counterintuitive behavior observed in ultra-thin films that challenges our understanding of material limits. So what exactly is this paradox? Ultra-thin films can store elastic energy far beyond what bulk materials can handle. These films don't fracture even though they exceed the bulk yield limits. Instead, they release this stored energy through three-dimensional self-rolling instabilities. In normal bulk materials, when you apply stress beyond the yield limit, the material either fractures or undergoes permanent plastic deformation. This is well understood classical mechanics. But ultra-thin films behave completely differently. They can sustain strains that are 2 to 3 times larger than the bulk yield strain without any fracture or permanent damage. Instead of breaking, these films release their stored elastic energy by rolling up into tubes, scrolls, or complex three-dimensional shapes. This is the paradox. They store impossible amounts of energy and release it in unexpected ways. This raises a fundamental question. Why can thin films sustain such enormous strains without fracturing? The answer lies in the surface-to-volume ratio. As films become thinner, the surface area becomes enormous compared to the volume. Surface energy effects start to dominate over bulk elastic energy. The film thickness is the critical parameter. Let's define our coordinate system and understand the geometry. Here we have a thin film with thickness h. The length L is much larger than the thickness. Typically, h is in the range of nanometers to micrometers, while L can be millimeters or even centimeters. Let's derive the elastic energy stored in a strained film. This is fundamental to understanding the paradox. The elastic energy density U equals 1/2 times the elastic modulus E times the strain epsilon squared. This is the energy per unit volume stored in the material. E is the elastic modulus, which measures the stiffness of the material. For silicon, E is about 170 gigapascals. For polymers, it might be just a few gigapascals. Epsilon is the strain, which is the fractional change in length. It's dimensionless. A strain of 0.01 means 1% deformation. For most bulk materials, the yield strain is between 0.1% and 1%. Beyond this, the material yields or fractures. But thin films can sustain strains of 5% to 10%. That's 5 to 10 times larger than bulk materials. This is the essence of the paradox. Let's work through a concrete numerical example using silicon nitride, which is commonly used in microelectronics. Silicon nitride has an elastic modulus of about 250 gigapascals. That's 250 billion pascals. The bulk yield strain for silicon nitride is about 0.002 or 0.2%. But in ultra-thin films, we can observe strains up to 0.06, which is 6%. That's 30 times the bulk yield strain. The bulk energy density is 1/2 times 250 times 10 to the 9 pascals times 0.002 squared. This gives us 5 times 10 to the 5 joules per cubic meter. For the thin film at 6% strain, the energy density is 1/2 times 250 times 10 to the 9 times 0.06 squared. This gives us 4.5 times 10 to the 8 joules per cubic meter. That's 900 times more energy density than the bulk material can handle. So how is this possible? How can the material store 900 times more energy than its bulk counterpart without breaking? This brings us to the role of film thickness. The key insight is that as the film becomes thinner, the energy required to create a crack increases relative to the stored elastic energy. In bulk materials, we use the Griffith fracture criterion. A crack will propagate when the elastic energy released exceeds the surface energy cost of creating new crack surfaces. The fracture stress sigma F equals the square root of 2e gamma divided by pi a. Here, gamma is the surface energy per unit area, and a is the crack length. But in thin films, the crack length is limited by the film thickness h. A crack can't grow larger than the film is thick. This fundamentally changes the energy balance. So we have A scales with h. As h becomes smaller, the effective crack size becomes smaller. This means the fracture stress scales as 1 over the square root of h. As the film gets thinner, the fracture stress increases. This is why thin films can sustain higher stresses. Now let's talk about how these films release their stored energy. Instead of fracturing, they undergo a beautiful self-rolling instability. Here's what happens. We start with a flat strained film. As the strain increases beyond a critical value, the film begins to curl at the edges. Then it progressively rolls up into a tube or scroll shape. This rolling releases the stored elastic energy. Why does rolling up release energy? This is a crucial question. The answer involves comparing bending energy to stretching energy. The stretching energy scales with the film area. It's the energy we calculated before, U times the volume of the film. Bending energy depends on the curvature kappa and the film thickness h. The key is that bending energy scales as h cubed, while stretching energy scales as h. The stretching energy is 1/2 E epsilon squared times L squared times h. Notice it's linear in thickness h. The bending energy is 1/2 E kappa squared times h cubed over 12 times L squared. Notice it's cubic in thickness h. For thin films, h cubed is absolutely tiny compared to h. If h is 10 nanometers, then h cubed is 1,000 times smaller relative to the linear term. This means bending costs almost nothing compared to stretching. When the film rolls up, it adopts a specific radius of curvature. Let's calculate this critical rolling radius. When the film rolls, the stretching strain is converted into bending strain. The curvature kappa is related to the radius r by kappa equals 1 over r. The bending strain at the surface is kappa times h over 2, which equals h over 2r. This must match the original stretching strain epsilon. So epsilon equals h over 2r. Solving for r, we get r equals h over 2 epsilon. This is the critical rolling radius. Let's calculate a numerical value for our silicon nitride example. Let's say the film thickness is 50 nanometers. The strain is 0.06 or 6%. R equals 50 times 10 to the minus 9 meters divided by 2 times 0.06, which gives us 417 nanometers. So the film rolls into a tube with a radius of about 400 nanometers. This is less than half a micrometer. These are truly nanoscale structures. Let's rigorously compare the energy of the rolled state versus the flat strained state. This will show us why rolling is energetically favorable. The change in energy is the energy of the rolled state minus the energy of the flat state. The flat state energy is 1/2 E epsilon squared times the volume 5. This is just the stretching energy. The rolled state energy is approximately 1 over 24 times E times h squared over r squared times v. This is the bending energy with minimal residual stress. Substituting r equals h over 2 epsilon, we get U rolled is approximately 1/6 E epsilon squared v. So the change in energy is 1/6 minus 1/2 times E epsilon squared v, which equals negative 1/3 E epsilon squared v. The negative sign means rolling reduces the total energy by 1/3. This is a huge energy reduction, which is why the rolling instability is so favorable. Let's explore some beautiful analogies that help us understand this paradox in more intuitive terms. Analogy 1. Rolled paper. Take a flat piece of paper and try to compress it lengthwise. It buckles and crumples easily. But roll that same paper into a tight tube, and it becomes incredibly strong and stiff. This is because bending a thin sheet costs less energy than compressing it. Here's the visualization. Flat paper crumples under compression, but rolled paper is remarkably stiff and can support weight. Analogy 2. A stretched rubber band. When you stretch a rubber band, it stores elastic energy. If you keep stretching, eventually it snaps. But imagine a rubber band so thin that instead of snapping, it twists and coils up. That's similar to what thin films do. Analogy 3. Fruit roll-ups. When you peel a fruit roll-up from its backing, it naturally wants to curl up into a tube. This is because one side was under tension while attached to the backing. When released, the differential stress causes rolling. This is exactly the mechanism in thin films. Analogy 4. Bimetallic strips in thermostats. Two metals with different thermal expansion coefficients are bonded together. When heated, one expands more than the other, causing the strip to bend. This is analogous to strained thin films where stress gradients drive curvature. For those interested in the rigorous mathematical framework, The behavior of thin films is governed by the Föppl von Kármán equations. These equations couple stretching and bending in thin elastic sheets. The simplified form is d nabla to the fourth, W equals F comma W. Here d is the bending stiffness, W is the outer plane displacement, and the bracket represents the coupling between stress and curvature. The bending stiffness d equals EH cubed over 12 times 1 minus nu squared, where nu is the Poisson ratio. Notice again the h cubed dependence in the bending stiffness. This cubic dependence is the mathematical origin of the paradox. As h decreases, bending becomes exponentially easier than stretching. There's a critical strain above which the rolling instability becomes inevitable. Let's derive this critical value. Rolling occurs when the energy gradient favors curvature over remaining flat. This happens when small perturbations in curvature lower the total energy. The critical strain scales as the square root of gamma over EH, where gamma is the surface energy. For silicon nitride, the surface energy is about 1 joule per square meter. Plugging in numbers, epsilon critical is the square root of 1 over 250 times 10 to the 9 times 50 times 10 to the minus 9. This gives us epsilon critical of about 0.003 or 0.3%. So above 0.3% strain, rolling becomes energetically favorable. This matches experimental observations beautifully. Let's discuss what we actually observe in experiments. These predictions have been confirmed in numerous systems. In strained semiconductor films like silicon germanium on silicon, we see spontaneous rolling when the film is released from the substrate. The rolled tubes have radii that match our predictions within 10%. In metal films deposited on stretched polymer substrates, when the polymer is released, the metal film rolls up. Gold and chromium films show this behavior reproducibly. Even single-layer graphene can exhibit rolling behavior when subjected to differential strain. These are the ultimate thin films, just 1 atom thick. This isn't just a curiosity. Self-rolled thin films have fascinating applications. Rolled microtubes can be used for drug delivery. The tubes can be loaded with medication, and the rolling process encapsulates the drug. They can be designed to unroll in response to specific conditions. The rolling transition can be used as an ultra-sensitive strain sensor. The onset of rolling is a clear indicator that a critical strain has been reached. Understanding strain limits in thin films is crucial for flexible electronics. We need films that can bend without fracturing, and this paradox shows us the fundamental limits. By patterning films with controlled strain distributions, we can program specific rolling patterns. This enables self-assembly of complex three-dimensional structures from two-dimensional precursors. This paradox has deep implications for how we think about material strength and failure. Material properties are not intrinsic at the nanoscale. They depend critically on size. Thin films behave fundamentally differently from bulk materials. Materials don't have to fracture. Nature finds alternative pathways to release energy, like rolling, that are less destructive. This suggests new strategies for damage-tolerant materials. The elastic limit is not an absolute material property. It depends on geometry, surface energy, and length scales. We need to rethink classical yield criteria for nanostructures. Despite our understanding, there are still fascinating open questions. Question: what happens at intermediate thicknesses where films are too thick to roll easily, but too thin to fracture normally? There's a complex transition regime that's not fully understood. Question: can we precisely control the rolling direction and final shape? For applications, we need deterministic control over the rolling process. Question: how does crystallinity affect the strain limits? Do single crystal films behave differently from polycrystalline or amorphous films? This is an active area of research. Let's compare this to other mechanical instabilities in thin structures. Buckling is similar in that it's a bending instability that relieves compressive stress. But buckling typically occurs at lower strains and doesn't produce the dramatic three-dimensional transformations we see in rolling. Wrinkling creates periodic undulations. Rolling is a more extreme transformation where the entire film changes topology. Wrinkling can be a precursor to rolling. Crumpling is chaotic and disordered, like crumpling paper. Rolling is ordered and reproducible. The energy landscapes are very different. Let's summarize the fundamental energy scales that govern this behavior. Stretching energy scales as E epsilon squared HL squared. Bending energy scales as EH cubed kappa squared L squared. Surface energy scales as gamma L squared. The ratio of these three energy scales determines whether a film will remain flat, buckle, roll, or fracture. This is the key to understanding thin film mechanics. Let me summarize how we resolve the strain storage paradox. First, thin films suppress fracture because crack propagation is limited by the film thickness. Smaller cracks require higher stresses to propagate. Second, bending energy scales as H cubed while stretching scales as H. For thin films, bending is essentially free compared to stretching. Third, rolling converts high-cost stretching energy into low-cost bending energy. This is why the instability occurs. Fourth, the critical strain for rolling scales with film thickness and material properties in a predictable way. Fifth, we can engineer this behavior for applications in self-assembly, sensing, and flexible devices. The strain storage paradox is a beautiful example of how geometry and scale can fundamentally alter material behavior. What seems impossible in bulk materials becomes routine at the nanoscale. This teaches us that intuition from macroscopic mechanics doesn't always apply at small scales. We must let the mathematics and physics guide us to understand these fascinating phenomena. Thank you for exploring this with me today.